Welcome to DevOps project demo. In milestone 1, we created a build server by using Jenkins. When the code is committed to branches on Git server, a webhook will be used to trigger a build job on Jenkins server. If the build succeeds, then this commit will be accepted. If not, this commit will be rejected, and also an email will be sent to the developer with the whole build logs. And also, the build server has the ability to handle multiple jobs according to different branches.
In milestone 1, we explored how to build a server. In milestone 2, we extended and analyzed how to test and analyze a commit. So every time a user commits, a set of basic tests are run and then to accept or reject the test. First, the lint check is run to see if it complies by the standards. Duplicate code is analyzed using duplicate analysis. Coverage of the code is analyzed using coverage tests. Custom metrics can be included as per the user's choice based on his acceptance or rejection criteria. And finally, a fuzzing component is added to see what percentage of unique rejected tests you can generate, and if the rejected tests are greater than a certain threshold, you reject it commit, else you accept it. Moving on, in milestone 3, we check out deployment. The configuration is first managed using Ansible. Ansible uses an Ansible playbook framework that runs a certain commands on a certain server before deployment. First up, the Ansible playbook uses a setup.yaml file which looks like this. First up, the packages are installed, then an SSH directory is created. Your private key is cloned into the SSH directory to ensure that you can pull and push commits from your GitHub. The bare repository is cloned. You create a copy of your post receive script. This script is actually a hook which ensures that every time this repository receives a commit, a clone would be created and the application would be run for sanity. This script ensures that cloning is done properly, the packages are installed, and the application is run using forever. That means any change that occurs triggers a restart of the application, ensuring that the app keeps running all the time. This is all about milestone 2 and milestone 3. Milestone 3 further includes components from milestone 1 and 2 to ensure that there is a continuity in the entire process. Milestone 4, we explore flame graphs and superfuzzers. First, we look at superfuzzers. Superfuzzers are implemented using genetic algorithms. The prime intuition behind using genetic algorithms is that when failed tests are evolved, this leads to more failed tests. This might help us to detect more unique failure test case than using regular fuzzers. The code is pretty simple. You first start off with the genetic algorithm. In the genetic algorithm, you generate a set of unique test cases. These test cases are all failed test cases. You then evolve these test cases using a standard mutation strategy. Two members of the population are picked at random and a single point crossover is performed. So in a single point crossover, half of the first parent and half of the second parent is combined to form a new child. The other half of the first parent and the other half of the second parent is used to form the second child. These children are mutated at a small mutation rate. For our experiments, we used a mutation rate of 0.5. That is, there is a 50% chance that a particular node can change to some other node. Since we are dealing with all discrete values, in this case, we use a discrete mutation strategy. That is, if a value does not belong to a particular set, we randomly change it to any other value from the particular set. We do not perform any kind of extrapolation to generate the new value. If this value has not been seen before, we add it into a seen set and then we evaluate it to check if there is a new member generated. If not, we ignore and we proceed. This is the general outlook of the genetic algorithm. This can be run and the results can be seen as follows. We included this as an npm script in our code. As you can see, genetic algorithm generated 275 unique test cases for 5,535 test cases, whereas for the same number of test cases, the regular fuzzing incorporated just around 53 unique test cases at almost the same amount of time. Thus, you can see that using genetic algorithms for fuzzing can help you detect more number of unique test cases compared to standard fuzzing using mutation.
So in milestone 4, we also want to use flame graphs to find the long chains of method calls in the code. Our test app is a Node.js smart calculator, which can evaluate infix, prefix, postfix arithmetic expressions. So the main idea is for each time we evaluate an arithmetic expression, we need to keep track of all the method calls involved. And then we convert such method calls log into flame graph log format. By using the tool provided by the inventor of flame graph, we can generate such flame graph. Now let's do a demo. So we created scripts to evaluate our app. So here we have 22 different arithmetic expressions, and we also have the script to process the logs. And now let's run it. So this is the frame graph from our test case. Y-axis represents the length of the function calls, the larger value of y and the long chain of the method call, and the axis represent the number of particular method being called. As you might see, here is a peak. That is what we are looking for. Now let's zoom in a little bit. The name of the function is factorial. Why? Because when we calculate factorial, we usually call factorial function itself. That's why it can be the longest method call. Okay, that's it. Thank you.